Okay, tonight we have a fairly good fire burning again. This is the 14th of September. And the same guy, I met him down at the restaurant. And yeah, there is a restaurant in Amanda Park, believe me. And there's a library too, you can believe it. If you blink your eyes though, you won't see it. But he says, how did your fire go? I said, that wood was green. He says, I got some dry wood. And so I paid him the money and he just dropped it off at the campsite here. And here we go. And in the book of Job, it says, as the sparks fly upward, so is trouble to man. Ain't that the truth? As surely as the sparks fly upward, trouble comes to man. Yeah. So, we had a fairly good fire burning tonight. We got other lights. And God said, let there be light. And there was light from a Coleman lantern. So, I got about as dim as it can go. Not shutting it off. I dare not turn it off any dimmer than that. Aren't you just enjoying all this, folks? I mean, isn't this great? Oops. Okay, this is Ranger Jim again. And we're back on the small battery. So what should our fireside chat be about tonight? What should the subject be? What should we talk about tonight? I see where Obama's ahead of both Romney and Perry in the polls. I guess Americans they're stupid, but they're not that stupid. I mean, especially senior citizens. When you got a guy saying that Social Security is nothing but a Ponzi scheme, I'd be very wary of an idiot like that. And Romney will never get elected because he's a Mormon. I mean, these guys believe in, well, they think they believe in what they believe in, but they're actually worshiping demons. I mean, come on, folks. Joseph Smith was in the occult when he got called by the so-called Angel Maroney. Yeah, right. One of you wrote me back about ham radio. And ham radio is nice. I can't get a signal where I am from my cell phone. Not a signal. But I can get through on ham radio. There's a repeater someplace around here in a mountaintop. And I got clear down to somebody, and you can look at it on the map. I'm here at Amanda Lake, or Quinault Lake, but Amanda Park, if you want to look on the map. They were down in Ilwaco. That's down really south on the Washington coast, south, extreme southeast, southwest. So, the repeaters are all tied together through the internet. So, but, you know, if that failed, I got HF. HF will go any place. Any place. Don't matter where you are. You don't need repeaters. And if you have code, so much the better. So anyway, as I was telling one of you, don't get into ham radio because of the end times. When when things get bad, everything's going to go down. Everything. everything. So don't even worry about it. Get into it because it's fun. And because it's a public it's called the amateur radio service. Did you hear that last word? Service. It's not the amateur radio hobby. The FCC categorizes it the amateur radio service in case of an emergency. Not an emergency then, when an asteroid hits, or when the Antichrist destroys America. It's too late. But before, during Katrina, things like that, The weather's been so bad back east that, it's really weird. It is really weird, man. We've had a beautiful summer on the coast. And they say it's been hot up here till I got here. But of course. And this campground was loaded. There's still a few stragglers, but most of them are gone. But we're thinking about renting a motel for about a week. Until the weather's supposed to get nice next week again, because we want to go up to the Olympic Peninsula on the coast and go in there. It's beautiful. I gotta stoke the fire. So anyway, when we got up here, there was a guy parked down there with a motorhome, and he had his generator running. And the first thought was, Jim, just let it go. And then I thought, no, we're not going to let it go. So, you always try the nice approach first. I knocked on his door, and he says, yes. I said, sir, I don't know how to say this, but, there are some of us that really like the peace and quiet, and we would appreciate it. And his wife chimed in. She says, oh, we're just using it to cook dinner, but after that, we wouldn't think of having it on. Wasn't that nice? There are some nice people in this world. There's a lot of jerks, but there are a lot of nice people too. And it always helps to try the nice approach first, What do they say? Honey catches more flies than, or how does that go? Whatever. And vinegar or something like that. Well, I still got a good fire going. It's probably a couple hours later. This wood was good wood. It's the night of September 14th, 2011. When you sit here looking at the fire, you think. You can't help but think. Man's been doing this for, if not thousands, tens of thousands of years. At least hundreds of thousands of years, and probably up to 1,000,000 years. Man's been doing this. Anyway. Oh, I like this. Coals. Red hot. Now you may think that's hot, but that ain't hot, folks. That's pretty cool. Yeah, that's pretty cool. When you're looking at the coals like that, not the flame, the coals, you're looking at what's called blackbody radiation. And this is not pure black body radiation, because some of it has to do with the make sure we ain't too close to the fire. Yeah, we wouldn't want to melt the camera now, would we? But let's just zoom in on them coals. If I can hold the camera steady. Yeah, I can do it another way here. Okay. Yeah, those colds are glowing red hot. You may think, man, that's hot. And it is hot. But it ain't that hot. I once knew a guy, he was a amateur astronomer like me, and he had a bumper sticker that said, well, one of them said, astronomers do it at night. And the other one said, red giants aren't so hot. What he meant by that is that stars are pretty much pure blackbody radiators. But you're seeing blackbody radiation here. And basically what's happening is the color that's given off, the radiation color, has nothing to do with the quality. It does somewhat. This is not a pure black body, but it has man, those are hot. It has more to do with a pure black body radiator. The color depends only on the temperature. It doesn't depend on what the material is made of or anything. It's also called the equilibrium radiation. I don't know if I can get into that. It's like there's a black body, it's like a cavity, and the outside of it, if it's heated, the outside of it will radiate in spectral lines, depending on what the material is made of. But if you drill a small hole and look inside, you'll see a continuum, kind of like a rainbow of radiation, and the shape of the rainbow curve, shall we say, depends only on the temperature, and it's a continuum. It's not spectral lines, it's just a continuum of radiation from all different colors, but the peak of the curve depends solely on the temperature. And at the turn of the century, last century, they knew this from experiments. And they tried all sorts of ways of coming up with a theoretical way of describing it. Go back out a little bit. They came out with all kinds of ways of describing. They tried to do it with mathematics. Well, it just didn't work. Because, and I'm not going to go into the details because it would take too long, but the mathematics proved an impossibility. It's like the higher the frequencies, the temperature, the color would shoot off to infinity, basically. At the higher, well, as the frequencies went higher and higher and higher, that basically what they said, there's no limit to the shorter frequencies have higher energy. And I know I'm not making any sense. I'm not making any sense to myself. But anyway, it didn't follow, the mathematics did not follow theory. Or the mathematics did not follow what was observed in nature. And it was about this time that physicists thought they had everything wrapped up. It was pretty much everything was done and we got it all down and this is it. Well, not so. Then a guy named Max Planck, a German, worked out a formula. Well, there was another guy called Wien. The first guys that did was the Rayleigh-Jeans, two guys, law. And it was no good at the high frequencies. I might have this backwards, but what difference does it make? And then there was Wien's law. He made it. It didn't fit the observed curve at the other end of the spectrum. So Planck got to work on it. He says, you know what? I'll combine somehow the two equations from the two curves. And he got close, but not close enough. And it was just a matter of changing, adding a -1 in the equation. It was kind of a complicated equation, but he came up with it. He came up with the right theoretical equation to describe the blackbody radiation. Then, but it was an empirical law, okay? Guesswork. Then he sought about to figure out the theoretical framework of how this equation would actually come about. And when he did, he found something really peculiar. He found out that the the energy that comes from anything, any kind of energy, is not continuous. It doesn't have a continuous, shall we say, range. It comes in little packets of energy called quanta. And Max Planck himself, he didn't understand that at first. He couldn't believe it. I mean, he just didn't understand it. He just wouldn't accept it. But this was the beginning of quantum mechanics. The reason is that the curve falls off at high energies or low or high frequencies. High frequency is high energy. Is just like a bank account. Some bank accounts you have to have a minimum deposit. Okay, the higher the frequency, the quanta, the photons, require a bigger minimum deposit. And finally it gets to the point where there's just not enough energy in the system, like this fire, to meet the minimum deposit. And so the curve rapidly drops off. Now the other end of the spectrum, it drops off too, and that's really complicated, and I don't completely understand it myself, but if you want a good book, it's written by a bunch of Japanese school kids, honest, and their idea is you don't try to learn something step by step. You learn it from the top down. It's called What is Quantum Mechanics? Just look it up on Amazon. What is quantum mechanics? And, you know, if you've had any high school math at all, you can understand this book. You're going to have to put a little work into it, but like all books, I read part of it and then go on to something else. Get through everything. So, I thought you might find that interesting. Black body radiation, coals. Yeah. Our sun falls right in the middle of the, there's a curve called the Hertzsprung-Russell diagram, and the hot stars are massive and blue, and they're massive, they're blue, they're hot, and there's not a lot of them. Our sun falls right in the middle, kinda, on this curve. And it's actually it's not really yellow, it's white. I don't know how to explain that either, but and at the very far end of the spectrum there is what they call red dwarfs, and they're cool. They're just like these coals. They're cool. They're very cool. And there's a lot of red dwarfs in the galaxy. They outnumber all the other stars. And they last long, too. They last probably from the beginning of the galaxy. So, the thing about red giants aren't so hot is when a star like our sun starts to die, it starts to burn helium at its core, and basically what it does is puff up. And as it puffs up, it gets less dense, and therefore it's less hot. It becomes reddish. And that's what a red giant is. And then eventually a red giant it becomes so big that its outer layers fly off because the gravity is so weak, because it's so big. And what's left is a core, and it's called a white dwarf. And we won't get into a white dwarf because it's hot. It's white hot. So, oh yes. So much for Astronomy 101. Oh man, it's getting late. It's almost 11 o'clock. The fire is still burning. That was a good wood. That's all the wood I got. I got more wood, but it's that green wood, which is no good. Oh. But I just keep thinking about Max Planck, how he came up with this empirical formula for blackbody radiation, and but then he had to come up with the framework. Well, it turns out in mathematics, I'm not sure this is the case with him, but I bet 99%, especially because the way quantum mechanics works, is that in mathematics, complex functions can be made up of simpler functions. In other words, a series of simple functions like sines and cosines can make up a complex function. And I'm just thinking on my own here, folks, because I get started on things I never read through them. I mean, they showed it, but it was a Taylor series, I think, that they used. They actually worked backwards or frontward. I don't know. Anyway, he had to work backwards. But no, that's what happens in mathematics. You take complex functions and you can make it up of simpler functions. And I'm not going to say for sure, but it's probably the fact that the formula that he found is composed of simpler functions like sines and cosines, which have discrete frequencies and things like that, that came up with the idea of quanta. There's another book, the Japanese, that would be a first book that I would start. It's called Who is Fourier? Fourier was a French mathematician, and he was the one that found all this, that complex functions can be made up of simple sines and cosine functions. In fact, that's the way all musical instruments work. There's no such thing as a pure tone. The only thing you can get a pure tone on is a synthesizer. But take out when you strike a piano chord. When you strike a piano chord, you get a periodic function, but it's not a sine wave. It's kind of jagged looking, but it's periodic. I mean, it repeats exactly. every cycle, but it's not periodic. Well, it so happens that it's made up of, I'm not sure if it's made up of just cosines or just sines or both. Depends on if it's an even or odd function of time or a combination of the two. But all those sines and cosine functions are called harmonics, or in music they call them overtones. And you can make up that complex piano chord being struck sound by adding up just simple sines and cosine waves. The only difference is they're multiples. Like there's the, like for the cosines, let's just say it's an even function of time, so it's made up of cosine waves. So then the cosines are multiples or even multiples of 2 of the original frequency, which is called the fundamental. So it's 2 and 4 and twice that and so forth. The sine wave, if you combine sine and cosine wave, the sine waves are made up of odd integer multiples, 3, 5, so forth. Am I getting this right, Jim? Yes, I don't got a book with me, folks. But I may be wrong on a few things, but I'm close. Let's put it that way. Okay. But the complex waveform is made up of all these sines and cosines of integer multiples, and it depends on all it depends on is what the relative amplitude of each one of them is. You change the amplitudes, you change the complex waveform, you change the sound. So you can blow the same note on a piano, or strike the same note on a piano chord, or in a clarinet. Same note, but sounds different because it's got a different mixture of cosines or sines or whatever with different strengths. So, yeah, get that book. It's called Who Was Fourier? Fourier. He's a French mathematician. A lot of the French were mathematicians. A lot of the mathematicians were French. I hated it when Bush got on his freedom fries thing. Dumbass. Wasn't for the French. No. So anyway, the fire, it'll go out pretty soon. And so will I, because I'm getting tired. Good night.